Hello, hello, what's going on? I'm Jun-chan. Welcome back to the stream. Yeah, sorry I didn't make it on Saturday. I wanted to do a review stream and then I got stuck into thinking about how to do it. And then in the end, the next day, I spent some time also trying to also continue thinking about the process of doing that and ended up not streaming. But it will come. It will come. Review streams will be a thing at some point. But right now we can just go back down to our graph Comonads and yeah, do a little bit of our housekeeping here. Right, so last time we were working on a little bit of a tiny rabbit hole here. We were working on the non-empty graph, and working on a non-empty graph makes a lot of sense for graph Comonad because Comonads always have a value on hand to return. So it makes sense to see this as some kind of focused value or some kind of non-empty container because you always have something to grab, right? So non-empty graph fits that purpose. And so that's why we're trying to build up the non-empty graph side of things that is present in the original algebraic graphs library in Haskell, and trying to port that into Purescript. But on our way to do that, we bumped into the following. So non-empty would implement something like vertex set. And vertex set, as it's defined in the original library, is actually vertex set right here. It returns a set. And so it returns a set from a graph, but this graph is the local graph, which is the non-empty graph. So why does it return a whole set instead of a non-empty set? Well, obviously a set is a bigger thing than an empty set. So you can absolutely return a set, but it feels just slightly unsatisfying. And so I've been trying to write it as non-empty set. And writing it as non-empty set means trying to reuse 4G in the way that it's intended. And so what that means is that 4G here makes sure that being passed different construction functions is able to take a graph to a result B that's able to derive that it's going to basically fold the B together. Actually, that's interesting. Like, are we folding the B or no? Right, we know how to create a B from a vertex, and then we know how to transform overlays into a B and connects into a B. And so that's sufficient for us to be constructing constructing Bs from these algebraic leaves of connects and overlays and their leaf content vertices. So sorry about that. So 4G helps us do that, and we can indeed return a non-empty set from a vertex by using this animus function, which creates the singleton, the non-empty singleton. We could use a singleton here too, I think. We just need to use the right one from the Purescript non-empty library, which is hovering somewhere, I think. Not here, not here. My tabs are out of control as usual. Non-empty. Singleton is here, and yeah, but it takes a plus instance, which is quite interesting. Plus extends the alt type class with the value that should be the left and right identity for alt. So, and I think we can derive a singleton from monoid F too. which is the way we went here. And the fact that this chooses plus instead of monoid is an interesting question, in fact. Isn't it? Maybe I could ask this in the repo. That semi-group thing, we've used that. Semi-group instance for non-empty. Oh, that's been merged. Not my code, but I don't know, it's open, it's not merged. So maybe maybe no real feedback on that for now. Let's see. That's, yeah. Okay, maybe I could ask in the Discord. Right. Okay, let's see. Where is the Discord? It's here. We can, yeah, maybe we can sort of restart a bit of a chat here. And oh yeah, I'm going to send my stream. Boom. Just a little bit of self-promotion. And what? Oh, wow, that's pretty cool. The feedback loop is pretty rapid. I'm streaming with low latency. What am I saying apart from blah blah? Right, I wanted to ask in code, is there any reason why oh, I didn't copy that properly. Singleton uses plus as the superclass to use empty rather than monoid. To and use empty. Okay, so that's a question, and yeah, so we rewrote basically singleton, right, as adding the vertex x in on top of the empty container. In our case, the empty set. So non-empty set is just this element on top of a regular empty set. That's the definition of non-empty. And then we want to just append our branches, either overlay branches or connect branches, using the monoid instance, or the semi-group instance more precisely, and that's what leads to this. So let me maybe bring the things we need into this new window. How about that? So we were talking about non-empty, so let's have empty with us. we'll need the alga thingies. And then I was just talking about this guy and the corresponding pull request. And that's exactly what I meant to be looking at right now. So the fact that to have a semigroup instance on non-empty is possible if you have a semigroup instance on the F, as well as an applicative instance on the F. And so careful, like the rabbit hole goes deep. And therefore, I'd like to be able to use append from the semigroup instance on non-empty so that I can get my non-empty set by just appending the elements of X. And append for sets is just set union. So basically would be unioning our set as we go. And as I say that, I have the ghost of Kmet kind of telling me that this is probably hugely ineffective. And I don't know why, but like union find algorithms start to, the keywords start to pop into my head. I don't know whether that's relevant or not, but anyway. So we union those branches until we get a set. And so unioning those, I mean, unioning a non-empty set is basically just unioning a set, right? It should be really easy. But in order to do that, we need to be able, and as I say that, I realized that I could simply create a dedicated append prime here that would do what we want. And that's probably the easy way to get out of our predicament. But since we have had some advice on how to solve the problem in a more general way, and that is a good way to learn, we're going to also do that. So what we really want is a function that goes from two non-empty sets to a non-empty set. And probably the way we would do that is by just you know, taking our A out of our set, which would be A's, and a B out of some B's, and then we would basically we would do like we need a non-empty thing. So if we have an A, then it will arbitrarily go at the top, and then we'll create a set by, well, unioning the A's and the B's. We could actually append them here because we do have a semigroup instance on sets. So we append it and with B's, and then we kind of insert, and that's the set insert. We need probably to import set as set. We have set as set. Okay, good. Boom. Where am I? I am lost in append prime. So set insert, and set insert is takes an A first, so we put the B here and then we append the A's and the B's, and I think that should type check. It looks like it does, but it doesn't teach us what we'd like to know. And what would we like to know? We'd like to know how we could make this the actual type append from the type class semigroup. And well, the problem we have here is that we're almost there, except that for deriving a semigroup instance for non-empty, we don't only need a semigroup instance on F, we also need an applicative instance on F. And here lies the rabbit hole, since set doesn't have an applicative instance. And going into trying to find why set doesn't have an applicative instance turns out to be a pretty interesting rabbit hole, really, because It's the same reason why set can't have a monad instance, and it's the fact that it carries an odd instance on its constructors. So let's see if we have something that explains it in more advanced terms, or more or less advanced terms. Applicative set. There we go. Applicative instance for set. Instance is almost correct. Okay, so no, that's just a Tory example with a very different definition for set. Here though, there we go. That's the explanation. The sets in data.set require that their elements are in order, which prevent them from being a functor. And that's mostly because, yeah, for instance, the map instance or the map function requires ORD, and a bunch of constructing function for set require ORD. So let's see if we can find some of those. So that's set monad, and we want that for sure. That's kind of where we're heading. And regular set is right here, and regular set requires ORD pretty much right out of the gate. To create one from list, you need ORD. And I think just to insert, you need ORD. And well, so it's interesting to think about whether a mathematical set needs ORD. And I don't necessarily think it does, but does it need EQ? That's another really interesting question. And right, so the idea is like if you have a set of, let's say, a set of numbers between 1 and 10. That's maybe not a good example, but let's try it. Then if you put a 1 in it, then now you have a set with 1. If you put 2 in it, you have a set with 1 and 2. Now you put another 1 in it. So is that a mathematical thing to do? Do you have another 1 that's lying around to be putting in? That kind of is a question, right? And then, okay, let's say you did find 1 lying around. Then you put the 1 inside the set. Then what Haskell is kind of saying here is that you need to be able to compare the 1 with the existing 1 in order to know that you don't have to add another 1. So meaning you need some notion of ORD, which is really, I think, a performance question, or EQ, which is not performant, but would allow you to then decide easily whether you have a pre-existing number, a pre-existing member that therefore doesn't need to be, that means that you're actually doing a no-op. But I think maybe that's really the more software engineering side of things. In math, I don't know if you really need to think about this unicity of the members in that set in that way. And that goes a little bit beyond my pay grade in terms of math here. But whatever it is, if we look at it in a pedestrian way and we're like, well, we have insert, and insert requires an ORD constraint, well, then it just happens that that's the reason why we can't, and I'm going to also get that guy here. The fact that we have this ORD constraint, like in insert and map and whatnot, means that we can't construct a monad. And we can't construct a monad, we can't actually construct an applicative instance either. And that is more of a problem with the way that type classes work in Haskell, that you can't really add these additional constraints there. And I think it wouldn't be like that with maybe a more sophisticated constraint language, maybe. But some smart folks have found a way to make it work with current Haskell, and but using JDTs. And so using JDTs, you're able to create a set type that will have this applicative instance there. And it's able to only impose its ORD and EQ instances when it really needs it. and that means the moment where maybe you query, or the moment where maybe you insert, is the moment where you're going to be asked for that ORed instance. So you can create that generic type class and then draw an ORed instance from the specific concrete type that you're using in your code base. So yeah, I'll drink a bit. Okay, so how does this whole thing work though? Well, yeah, it works with GADTs. So so it allows you to basically refer to a prim type, which is the real underlying set data type from the containers library that we were looking at here, from the containers, but wrap the rest, or wrap constructors around it to manipulate the set in something that looks a lot like a monad instance, which is actually what we want. And actually, I'm not sure whether I should be doing set monad, or is it different? The applicative thing, is that from a different? No, it's not. Where is the applicative thing? Maybe it's not even. No, it is. Okay. You just have the monad and you get the applicative for free here. So it could be that we could create a simpler, we could create a set applicative that would mean that we'll have less work to do by just having to define pure and app. And app isn't app plus. Yeah, I'm pretty sure app is going to end up being plus. That would considerably simplify the amount of work that we need to do. So that's an interesting thought. So maybe that's a good place to aim for this stream. And then, in fact, well, we'll see where we go, because there's a few things that we need to apply from a response that we had from the smart folks at the Purescript, on the Purescript Discord. So maybe we just try that, and then possibly we could just simplify and remove the bind and zero instances. I am quite tempted to just start with that. Start with removing the bind questions, because that's very complex. As you can see, it's actually the source of most of the complexity here. And I think that's the way that it, yeah, but then we need to also not have zero. And so here, and then it compiles. And then we would have to implement only a subset of things to actually make it work. So let's crack on with that and see how far we go, because we only really need the applicative instance and the functor instance. Why are these things imported qualify? That is a fairly rare thing to do. Control applicative. Okay. I think that's in Prelude for us, so we don't really need any of that stuff. And then map. Oh, that's implemented in terms of lift m. And lift m, I think, is really something you get from the monad instance. But maybe we'll work it out. Yeah. I'm not so sure we'll work it out, but it's interesting. I think we'll learn something if we do that. Pure. Pure is set singleton, right? So let's open up the regular Purescript sets. I think we're going to need that set from Purescript. And okay. Yeah, that doesn't work. That's sad, but it's okay. And set. And that's I believe set from yeah, from containers, and then we say yeah, singleton. So s.singleton would be pure. And then this is S union, really. And then oh, but yeah, no, it works for all A. And then union, does this require the ORD instance? I think it's fine if it does. It does require the ORD instance. No, it's not fine if it does. So that's the place where actually it can't be done that simply. And then map, I think, yeah, also requires the ORD instance. So we have a s.map, but it's not going to work for us. So, but that's cool. It means I haven't understood what the trick is to make this work properly. So let's stare a little bit at that. Well, is it at the documentation or at the code? Yeah, map has those constraint with ORD, and here with functor set, we are not constrained with ORD anymore because we use lift m. And I'm just a little bit unclear about where lift m comes from. So let's look at the type of lift m in Google, maybe. Lift m takes a function from A to R, and yeah, so it's really map, but for something for which you have a monad instance. So I think, yeah, weirdly enough, even though I thought that you could get rid of the monad here, or to try and simplify it, everything, the workhorse here is the monad instance. I think it depends on that definition of the monad instance right there in order to create those more simpler instances for functor and applicative. So let's just go for it. We can't simplify, so let's just go and try and implement the trick that the smart folks have given us. And yeah, that's of course app. And this lift m, well, it doesn't exist here, but I think it should exist generally in the world somewhere, right? Lift m, lift m1, okay. Lift m1. Lift m1 should be fine, and app, right, because yeah, because it depends on apply. And so instance apply set where app equals S union, and we just need to import apply. Is that what it is? No, it's apply, not app. And then here we don't have a monad instance, and indeed that's correct. So let's start writing it, and we need a bind instance in Purescript, and that's really going to be bind. And it's not return. What is it then? Is it just pure? Oh no, yeah, right. We don't have to say anything, I think. Is that right? It might be. Yeah, we just need bind and applicative, I think. And so why is this not working? Maybe because of how we define bind. And that's kind of one of the ways in which we are going to have a problem. So mapping, so bind is supposed to take an MA and a to MB and give us an MB. But clearly here we have a tuple. So we need to take our A and our F, or our X and our F, and we need to pass them to our bind at the very least. And then we're going to have this type mismatch, I think, because of the existentials, and that's where we go back to the little chat that we've had at the end of last stream, and which continued a little bit further, and I think holds the key. So let's go and look at it again. So I was asking how to do things. Joseph first guided me to gadgets or GADTs, and then I mentioned, but I couldn't find how quantification or constraint work. And then Nate said that what's happening is that I'm actually using existential quantification here, not type equalities, meaning it's not really about the Leibniz trick, the Leibniz equality trick that's used in the different approximation of gadgets talks, where the idea in those approximating gadgets here is the use of these added constraints here at the end of the constructor to pass a proof that your A has the correct type, or the correct return type, more importantly here. So saying that if you input 2 ints, then your return type would be an int. And you carry the proof of that, and that allows you to then get the int, the expert int that you want on the use site. So that's all very well and good, and a great trick, and I had seen that, but I didn't know how to understand the trick that is in the code right here for bind, which is this set A to set B to set B. And here we have a B and an A, and it turns out that actually that A is not the same A as here. So it's a bit of a trick, meaning I think, but the B here is the same B as is really A, I think. It's a little bit tricky to understand, but let's refer to what Nate said, because maybe that will help us to understand what's happening here. I would look at how to encode existentials with for all, right? So really what Nate is saying is the pattern we have here is not something about type equality. It's something about an existential being encoded somewhere here. And so, you know, that led to me, I think I was already trying to implement something like that here, but there's actually a particular way to encode existential. This is really a universal quantifier. This is attempting to say for all B, but really apparently what this says is there is a B, or there is an A such that blah. So Joseph gets back saying, boom, like giving the solution, basically using this transformation, which is described in this Stack Overflow post that Nate then copies. So it's how to express existential types using higher rank n type polymorphism. And so it's like, okay, but what? Oh, I see, I say, half understanding. So in the Haskell GADT, this is actually an existential, this bind thing. And so Joseph says, yes, it's confusing because there's 2 different A's. So there's a lot of different A's, so that's confusing. And then it's an existential because the A does not appear in the final set B. So, okay, so that's what I'd like to try and understand here. The A, I suppose you mean this A, does not appear in that set B. And so for some reason, that would mean that there exists an A. It doesn't have to work for all A's, which I think if it has to work for all A's, then it's a super small space of functions. connects to like natural transformations, I think, and the fact, and like identity function. Like if you have for all a to a, then there's only one implementation for that, and it's super generic, and it really just passes things forward because it can't do anything else. And so if you implement this kind of constraint there, then that makes this function maybe too small. Whereas if it's an existential, then you're just saying that you have an a maybe, and so you're given the a maybe, and then you, out of that a that you're given, you can end the function from an a to, then you just return some b. So maybe that means existential. But maybe we need to also read a little bit more about existentials just to get a little bit more fluent with that. Existential types. Normally when creating a new type, blah, 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 every type variable appear on the right-hand side, but also appear on the left-hand side. Existential types are a way of turning this off. Okay. So existential types can be used for several different purposes, but what they do is hide a type variable on the right-hand side. Normally, any type variable appearing on the right, but also appear on the left. So let's see. In a non-JDT context, that's going to be easier to understand. So data worker XY, worker buffer B. Buffer B is not on the left side. So where do we get that B from? Becomes the question, right? This is an error since the type of buffer isn't specified on the right. It's a type variable rather than a type. But also isn't specified on the left. There is no B in the left part. In Haskell 98, you will have to write worker B XY, give you a worker buffer B input X output Y. That may or may not be an actual problem. So can we map this exactly to this bind? Yeah, maybe. Because I suppose what we're saying is like we get a set B, but where is that B coming from? So, and we don't want to define it here. So, okay, yeah, I think that means that there exists a B somehow, right? Okay, so, but okay, the important bit here is, as Nate said, the B doesn't exist on the return side. Is it on the left hand side? I think it's a slightly different case for us, isn't it? Because what does this mean if we wrote it as a constructor? Then that would be, and that, let's say there would be only one constructor. There would be something like bind set A to set B, and that's it, right? To set B, and that would be maybe a B here. So it's confusing because of also the mix and matching of the A's and B's. But because we return a set B here, we can imagine that this is really the B that we return. And therefore the question is, yeah, but where did this A come from? And so that's how it maps this buffer being lacking here, is that we need to come up with an A. Okay, and let's reread how Nate phrased it. He said, it's an existential type because the A does not appear in the final set B. A does not appear in the final set B. The way that B doesn't appear in the final worker XY. Okay, let's this is the same as B not being in worker XY. Not appearing is the same as B not appearing in the final worker XY. That's worker XY in this example. In the Haskell wiki page for existential types. Boom. Okay. So that's one thing. And then what? And then what's the solution? Usually there's no problem at all with the state of affairs, which is why Haskell 98 works this way. However, suppose that worker can use any type B so long as it belongs to some particular class. Oh. Okay. Then every function that uses a worker will have a type like foo buffer B to worker B int. Oh, you mean it's not a problem to have B here? Is that right? Okay, it's not a problem if you have a B. Okay, because then you just have B, but it means that you need to carry the constraint instead of maybe encapsulating the constraint. Is that what it means? In particular, failing to write an explicit type signature will invoke the dreaded monomorphism restriction. I see. Well, I mean, this is part of these things that I bumped upon many times, but I never quite know what it is because it's mostly a compiler quirk, if I understand correctly. So it's about something that if you don't specify the type signature, this yields blah, but this doesn't. Instead, F2 is unit to string. Whoa, really? That's a little bit crazy. You can fix it using explicit type signature. So thanks to the monomorphism restriction, that sounds cynical. Difference between the first and second version: that first version bind X via function binding and is therefore unrestricted. Second version does not. Yeah, you know what? Let's not go further down the stack of rabbit holes. Using existential types, we can avoid this. Okay, so data worker XY, then we put the for B, buffer B, constraint, and on the right hand side, and then put the B there. And then all of a sudden, we don't need to have B's here anymore, and foo can be a worker, can return worker int, or foo, or value foo can have worker int. And the type of the buffer now does not appear in the worker type at all. And that feels a bit like this encapsulation in the st-monad trick, which maybe this is an example of st-monad existential. Is that right? Existential S unique identifier. Any state that could somehow smuggle out this modic action would necessarily be an existential type. Basically nothing you can do with an unconstrained existential. Okay, I'm learning something new here. There's nothing you can do with an unconstrained existential. That's what we have here. We have a constrained existential, and it's introduced specifically with this question of constraints. But here we don't have a constraint that I can see. Is that going to be a problem for us? And but there's no constraint here either. So maybe it's fine. The fact that we can't do anything with an unconstrained existential maybe is not a problem for us. don't know, but it seems like it is that same pattern, right? For S, I don't know, yeah, here. That's the run, that's the for all, that's a higher ranked type, I think, here, or maybe a higher ranked constraint. Yeah, I'm not super existential type and non-transformers. If we have a changing state monad, we can define an existential quantifier. The existential monad. Okay, this is this is a bit. I don't think we need to understand that necessarily to go forward here. So the type of the buffer now does not appear in the worker type at all. Yeah, and this has a number of consequences. First of all, it is now impossible for a function to demand a worker having a specific type of buffer. So I suppose it means that functions need to work for all buffers, I suppose, which sounds more like universal quantification, but maybe maybe it's about where the constraint is on the caller or on the callee or something. Second, the type of foo can now be derived automatically without needing an explicit type signature, so no monomorphism restriction, okay? And thirdly, since code now has no idea what type the buffer function returns, you are more limited in what you can do to it. Yeah, I think that's similar to it can't demand to have a specific type of buffer, therefore it doesn't know which type of buffer it has, therefore it can only work with basically the methods of the buffer type class. In general, when you use a hidden type in this way, you will usually want that type to belong to a specific class. Yeah. Or you will want to pass some functions along that can work on that type. Oh, otherwise you'll have some value belonging to a random unknown type and you won't be able to do anything to it. So that's exactly what that thing I closed was saying. If you have an unconstrained type, there's basically nothing you can do with it. Yeah, and I think it is about the responsibility. The fact that it is about like some kind of higher ranking thing, I think, like the fact that you smuggle a for all or a constraint inside the side of something that that will end up being provided. It means that you need to deal with anything that could be provided, and if you have no constraint at all on the B here, then I suppose you need to make things work for really any B. And I don't know if it works for us here, but whereas if you, meaning you can't, you have the B and the only thing you can do is pass it along. But in our case, maybe that's fine because yeah, as long as we can extract, we know we have a set of B. So in our case, it's actually totally fine because we have a set of B's. If we know how to get a B of interest from that, then we just pass that B to the function we also have, and then we get the set of A that we want to return. So that's actually all good. Where it's interesting is that in a monadic, if it was the monad type class, this is exactly where, in order to get a B of interest from set, that's kind of where you'd want to pass maybe the return function somehow, or you'd want to pass the monad type class so that you have access to return, which allows you to get a B out of the set of B. So maybe that's going to introduce complications for us here. But I'm starting to maybe understand a little something about this, and I feel like I should write something here about it here. Existential types. Boom. Okay, or not. Yeah, and I think I can copy it here. Okay, and so in our case here, here for bind, A does not appear in the returned type set B. And I should write what I wrote here. That makes it, I think, easier to understand. Okay. So it is for like whether we need to smuggle for inside or not, I do not know yet. But with bind, we seem to have done no, not exactly. So maybe that's fine. Okay. Okay, so I think that's all right. Having a unconstrained though comes with some warnings. For instance, not this guy, but here. Poof. And poof. Rank 2 polymorphic. Any state reference that you can somehow smuggle out of necessary existential type. There's basically nothing you can do with a constrained existential. I love this little aphorism. And similarly here, yes. Yes. Another copy paste mistake. Also in the Haskell wiki. Boom. So here, if we have a set A where A could be anything, then our problem would be to get an A out of set A to pass it to A to set B, to the A to set B we have lying around, to use an approach I've heard Ed use for this. And and that seems to mean that we'd want a monad instance on sets at face value. On set A, so that we can just return set A, right, and get RA. But how do we do that here? Note you can use existential types to convert. So what the Haskell wiki says is that we could want to pass along some function that can work on that type. And now I'm wondering whether the trick that is given to us right here, first by Joseph and then by Nathan, this kind of CPR-like transformation, whether that's what we want. So let's get that under our eyes and say set. So which is which there? B returns an A. So I think if we want to do that, then we can maybe instead do A returns B, have the full A, and then say data set B. So Joseph and Nate propose this. Blah, 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 blah. Yeah, this crazy transformation via this Stack Overflow post. This guy. Via this. Okay. So is that somehow passing some function along that can work with this type, or is it something completely different? So here what this says that, well, first of all, apparently we need to say that now instead of having a set A and an A to set B lying around, we say that we have a function that if we have those lying around will return us an R. And maybe doing this inversion of control allows us to recuperate our ability to not have return, maybe, because then we can implement that function us rather than wait for someone to implement it for us, maybe. But anyway, so if we have that function that returns an R, then the moment where we get the set A and the A to set B, then we get on R and we're done, sort of, I think. And that R doesn't need to carry a lot of information, I don't think. I think it can be something like unit, and then it's really just an inversion of control trick. It's like we're waiting for, instead of being given this set A and A to set B function, we write the function that, given those, we return that unit, maybe, and then bind is the thing that then will just pass along the set A and A to set B that it has lying around, execute our function with it, get the unit, and then be done, something like that. or know what to do with that unit. I don't know, maybe know what to do with that. Oh, so no, so it's not unit. No. It's a thing that then can be returned in order to create our set B, right? Yeah. So if that thing, then that particular function then requires some constraint, then we can pass it along there. I think that's the idea. It's like the inversion of control is that we can decide to add the constraint here, and then we don't have to write it in the data type. Something along those lines. Let's see if we have more to inform us here. Blah blah blah. Pretty ugly to use. Confusing because there's two different A's. GDTs are existentials plus type equalities. So yeah, so okay. And type equality bit is the one that's described here, but the existential is not described. But yeah, it's existential because A doesn't appear in the final set B. So A is existentially quantified. Yeah. It's confusing because the A in data set A has nothing to do with the A in the constructed signature. Yeah. And then to make it work with constraints, do we have to verify them? Ah, yeah, because I thought maybe I needed to get pass ORed here, maybe, but I'm not even sure whether I need to pass ORed. I think the reason why I was asking myself that is because I think the type error that I was getting, and apart from this mess, was something that led me to think yes, that I was missing an ORed instance on my S somehow. But it could be that this is just a crappy question. Although the answer does show that if I wanted to pass in something with a constraint to my inner type, then I could. That would be an existential encoding that takes constraints. So which I suppose is exactly what would mean a constraint, maybe yeah, here. Yeah. So possibly I could pass ORed here, but I don't know why I would want to pass ORed. And it seems like my instinct is more like, oh, but I need return in order to get an A out of set A. But this might not be. It could be that it's not needed because no, I have no idea. We do have access to empty. We're working on sets, so this doesn't need to be so general. So empty, yeah, right. Empty is a valid A you can get out of set A. It's a bit restrictive, but we could ignore the set and return empty. Maybe that's actually what we have to that's what we have to do if we don't have constraints. If we have constraints, and maybe we need constraints because we need to run map here. Yeah, but no, I think there's an issue here as well. So interestingly enough, Joseph immediately also translated prim as a with this encoding. And I think that's probably an important hint here because we have trouble getting that ORed constraint, which my feeling is that we should be able to just get the ORed constraint from prim S. But I think because we don't really have GADTs, I think we need to pass the ORed constraint in that way. And yeah, so let's do it. Let's do this, and let's follow the types and see whether we can work it out with the compiler helping us. And we'll need to do the bind. As well. Okay, here we go. We're in the new world now. And right, so now we're receiving different things now, because when we pattern match on prim, we really have a S that expects, we have this crazy function, and we have a set A. No, that's a set A. So we have this crazy function. What do we apply it to? Would that even work? Or do we need to actually add this here? Do we need to pass in order a set A to R function to run? Okay, I'm a bit confused. Okay, right. Okay, let's read the Haskell, the Stack Overflow post. Sigma types. Just type pi types generalize our ordinary function types, allowing the resulting type to depend on a value on its argument. Sigma types generalize pairs, like the type of second component to depend on the value of the first one. Right. Which maybe makes sense in like the simpler sort of like that where is that sti a where sti int right, s int sti int to int, no, s int is int, yeah, that thing, is bool is bool. So there we're saying there's a pair because if we have a, so what is it? I was just looking at the 2015 Lambda Conf talk from Richard Heisenberg on GDTs, and it had a thing like that. And the pair would be here. When we pattern match something that is an S int, that therefore would be sti anything, then we can get 0. And that's the dependent pair here, I think, which means that it pairs this with 0, and then it pairs sti. Oh, yeah, no, okay, of course, as int, blah, and then as bool, blah. I think this is it. Yeah, I think this is it. Yeah, and that's bool. We'll have a bool here, and that would be false or something. And so yeah, so the pair has type sti int, and that has type sti bool. And so the type of the first argument determines the type of the second argument. That's what I think this means. Like the type of the second component depend on the value of the first one. The value of the first one, in fact, yes. Yes, because you could say they're the same type. They're just sti a. Possibly, you could say that. Okay, and then what? In a made-up Haskell-like syntax, sigma type would look like this. A is of any type, and B has a type from A to a type. And then the first function, the first part of the pair would be of type A, and then the second will be able to be a type B that waits for an A in order to know which type it is. And then this pair AB will be defined with a and then a dependent thing that just returns some B. Oh yeah, that would be a special case where you always return B instead of pattern matching on a value of the type A in order to get the type of B. Assuming star is of type star, can define exist AA as sigma blah ADA. Oh, okay. Oof. Okay, exist AA is something that takes anything okay, I think that's so any type. It's inconsistent. Ah, yeah, it's okay. I think this is like a foundational question. It's like a set part of itself, the set of all sets, part of sets, like big sets. So we're saying star or set is of type star, just as a simplification, I think. And then we say, well, sigma take anything, and then a something that given that thing will return the thing. Okay. So the first component is a type, and the second one is a value of that type. Okay. Oh, right. So foo sigma int 4. Okay, yeah. So that's dependent types, right? But in this pair way, like I suppose pi is when it's not when it's in a function type, like it's a return thing. It's like A we return a B, whereas here we have a pair of A and B. I think that's what the difference is. And so exist AA is fairly useless. We have no idea what type is inside. So if we get given one of these things, I don't understand. If we're given a sigma int 4, do we really not know what type is inside? Not from its type signature, because it could have any value. And because its type is A, we don't know. In the way that if we get given a star A, we don't know what's in it until we apply it. I mean, isn't pattern matching it knowing what is inside it though? Only operations that can work are idle consts. So That seems a bit weird though. That's not a 4 is not a function from A to A here. So here we're talking about sigma intro, and we're saying sigma intro is of type sigma star A to A, which is a promoted lambda here, I think. And so second, isn't it const 4 here? Or is that just a type? Oh yeah, no, it's just a type. So it takes, this is second here. Well, it's B really, but yeah, it's B, and therefore second is B applied to first, so it's A applied to set. So it returns any element from the set that is being passed. So it's just the set and any element from that set. So let's say, yeah, set of ints or the set of chars and any element from that set. But apparently we have no idea what type is inside. Yeah, I suppose because this is not specialized, right? So those are value inside, and when you get that type, then you have no idea what type is going to be inside. Is it going to be an int? Is it going to be a char? So it's the same as is sti. And oh yeah, in this case you can't even pattern match, I think, because this is everything. Ah, okay, yeah, okay, I think I see what this means. All right, so in that SO article, sigma star A to A is exists AA. It says it's useless because we have no idea what type is inside. It's so compared to sti. I suppose I should get our guy over there. From Lambda Conf 2015, Richard Heisenberg, not Heisenberg, I think. And on Garrett's. Compared to sti, here we can't even pattern match because sigma star blah, well, because in blah star is all possible types. So I mean, couldn't we pattern match though in principle? If we could, if it's enumerable, I don't know, right? Maybe couldn't we pattern match if star is enumerable? I mean, we could partially match some enumeration in it and something that we know is in it. It doesn't even need to be enumerable, really. It just needs to have something we know that could be in it. And then we could pattern match an int and then otherwise return some other thing. Okay, let's say we don't understand. And so now we're extending this to exist a fa, or even exist a show a fa. If an f is star star, and the first case is sigma star f, or sigma star lambda a to fa. Second one is a bit trickier. We cannot just take show a type class instance and put it somewhere inside. However, if we're given a show a dictionary or type show dictionary, we can pack it with the actual value. So now we return show dictionary a fa. Inside is a pair of an fa and a show a dictionary. So I think that's this idea of you will want to pass some function along that can work on that type. This is a bit inconvenient to work with and assumes that we have a show dictionary around, but it works. Packing the dictionary along is actually what GHC does when compiling existential types. So we could define a shortcut to have it more convenient, but that's another story. As we learn soon enough, the encoding doesn't actually suffer from this problem. Digression. Thanks to constant kinds, it's possible to reify the type class into concrete data type. First, some language pragma and one import, constraint kinds, get signatures. Gadgets already give us the option to pack a type class along with a constructor, like so. However, we can go one step further with a dict constraint, blah. Works much like the BST example above. Pattern matching on the dict gives us access to the whole context CTX. 1 second, I'll be right back. Okay, so let's go for like 10 more minutes, I think. So pattern matching, dict context give us access to a whole context. So I think that's a way to, reify constraints. But maybe we don't need that, hopefully, maybe. We also get quite natural generalization of existential type that quantify over more type variables, such as exist AB, FAB, which, is really this kind of nested lambda thingy. Or we could use sigma just once, which is kind of like a currying style thingy. Okay, so now the question is, can we encode sigma types with just pi types? If yes, then the existential type encoding is just a special case. No glory, I present you the actual encoding. Sigma encoded, so there we go. So same type signature, except that here it's this weirdness instead of this a b first, which would require to have dependent types, right? Here we need to be able to call b on first, B being a type, first being a value, and we can't do that. But here apparently we maybe would be able to do something like that. So how we'd say X is of type A, and we pass X to, they return something of a type XB. I think I heard something. Oh yeah, no, nothing. So what? So hold on. First of all, is it what we have seen? What's been recommended to us, and I believe it is, right? So set monad or A, set A to R to R. Well, it's not exactly, because this is this special case of using this B that is on it, like I suppose the simplest dependent pair that people can come up with, I imagine. I'm still hearing some bleepy noises, and I'm not sure what they are. Oh, you know what they are? They're probably yeah, they're Discord. Okay. Singleton. Mono would be unnecessarily restrictive, as you need to do monoid FA, which places an additional restriction on A. Oh, yes. For example, this would mean that A would need to implement semigroup if we were dealing with maybe. Yes, yes, by using plus you can have a... Oh. That makes total sense. Thank you. A non-empty maybe A makes no sense. That's true. But yes, I get the idea. Wonderful. Such smart people. Okay. So, yeah, so we're not dealing exactly with exists. I mean, we are dealing with exists A of some sorts, right? I think we're trying to say exists. Okay, let's look at the encoding one more time here. Let's say if we say the prim version, we want to start with our feeble attempt, which was just this. Maybe there's a mistake here. Given an S set A, we get a set A. So here I think it's an S set A to R, I think. And the original Haskell GADT encoding is this. Hey, Lone Ranger, thanks a lot for the follow. Really appreciate it. Do you do some Purescript yourself? So prim. Yeah, so, okay, so in GDT syntax, we get this S set A and we get the set A that we want. So here we, in prim, we pass the S set A with our ORD and we get the set A. But here, though, I kind of wonder, though, is that the case where we need the existentials? Because with bind, it's clear that we do. So let me redo the bind thing. With bind, we're kind of trying to go from, yeah, this idea of like set B, B to set A, like so, right? But then we're like, actually we need to say exists B, I think. And so exist, yes, of course. So I see. So what the blog post says, or the Stack Overflow post says, is that exists B FB is sigma star B FB. So therefore our exists B and craziness with the A here, I don't know how that works, is really B to craziness. And that means then that since this is sigma, this is the payload for sigma here, this B, oh my, then it means that this sigma encoded thing, hold on, I can't even wrap my head around it. It's not this. This sigma encoded thing has X as a what? I thought this was a B. Hold on. Exists BFB. No, this is exist. This is exist A. What is this? This is not exist. This is something that you can build exist out of. Exist is this. Okay. All right. So that's exists. Right. So when we do sigma A and a B that waits for an A. Yeah, I'm not sure I'm actually even thinking about this correctly in terms of constructor and resulting data type. When I was writing it here, I thought that the first part of the pair was the end type, or the value of a value that you're given with that that generalized abstract data type, and then that somehow the B function or the B type level function would take that value and return a value that would have a type that depends on the type of the first value, right? That's the definition here. But then I was a little bit confused when I was trying to think about it in terms of pattern matching. So I'm not even sure whether I'm getting this right or in the right order. Could it be the reverse? Is that the first thing is maybe like this int, and then based on that int, then I get the type st int. Yeah, maybe. But if I have a number in there, I can get, if I have a number of a known type, so therefore let's say I have value 4. No, first is the value 4 of known type int. Then this GADT takes the value, has a function that takes the value 4, has a type that, given the value 4, is able to return some other type. It sounds like I need to do more dependent types, maybe. Well, we're trying to understand this encoding, and if I don't understand everything about the encoding, maybe it's okay. So let's try and go a little bit further and see where we land. I mean, this has this kind of continuation passing style transformation, and that's what we think we recommend it to do, maybe with our data type here. Whether we need to do it for set A or not, that's unclear. Maybe we do, just to be able to pass the constraint. For bind, we clearly do, because we need to have a B. So that seems like that's a different reason. So not sure we need the existential encoding here, just for the ORD constraint, since we don't have an existential A. So I might, I'm not sure here. Here we need the encoding for B. But what about constraints? I do not know. This seems like a bit of a mess. I'm going to delete it. Okay. There are some interesting parallels. Independent pair represents existential quantification, and from classical logic we know that blah for our R is almost bottom or false. So with a bit of rewriting we get blah, which is this CPS transformation, which, by the way, I think it's Yoneda probably hidden. And finally represents universal quantification as dependent function, blah. And then the church encoded pair, you get a similar looking type, pair A to B to R to R. Oh, so that's a church encoded pair. Interesting. So it's a thing such that given if you have a function that knows what to do with an A and a B, I don't really know how to read this. I think I can read it in terms of continuation passing, right? Is that instead of having a pair and an A and a B right away, we have something that knows what to do when it gets the A and the B, which is, no, we have something that knows what to do when it gets past a function that knows what to do with an A to B and an R, and returning an R. Then we have a pair. Yeah. Oh boy, this is always bending my mind a little bit. This is kind of interesting perspective taking exercise. We just have to express the fact that B may depend on the value A, which we can do by using dependent function. Again, we get the same type. Corresponding encoding decoding function are blah. Special case actually simplifies things enough that it becomes expressible in Haskell. Let's take a look. By special case, I assume they mean the existential encoding as opposed to the general dependent pair sigma encoding. So right, so then I think we're in our case, the case that so what I deleted there was this attempt to try and do this, transform the general sigma encoded case to the special existential encoded case. And yeah, obviously I couldn't come up with that on top of my head, so I don't feel so bad. But so here we're saying exist encoded is this, and I think that's just a way to say what we're doing with the constraints. And that just looks pretty much exactly like what we want. I mean, the show constraint there seems to be dropping from the sky, except that maybe it refers exactly to an example before. I think it refers to the one with show dictionary there. So it refers to this. No. So of course the question is it an existential also here? Which leads to this, and I still can't decide. Okay, so let's write this as a question for next time. Okay, graph Comonad, and has vertex, non-empty set. Yes, so implement set monad in Purescript, which means encode GADT existentials in with sigma encoding. And then to do that, we need to figure out, like, do we encode only bind, which we know we need to encode, or also prim? So that's I'm a little bit confused about. And so I think we can start by saying, let's just encode bind and see where that gets us. With the order. And then that leaves the complexity to here, where we know that bind now has this thing. And then the question is, who gives that function to whom? It feels like I need to pass it along here, which indeed is super ugly, but it might be where we need to do. So we'll need to play with a simple example of how to actually use these things, and maybe it's maybe it lies in the rest of the article here. We shall see. So that's, I suppose, another way that I could phrase the question for next time when we pick it up, which is how do we even use that thing, right? I mean, this is a mouthful. It's a mouthful, but the fact that it resembles the inversion control that we were dealing with Purescript Comonads, and that this is such a common trick that you see everywhere, and that I'm pretty sure it relates to. Does it actually relate two Yoneda? Let's just double check that. Yoneda and existential encoding. In system F, exist AP can be encoded as for a PBB. That's it. And then I can't prove that either. Can check that the analogous strategy failed. That encoding for exist is a consequence of Yoneda. T for a TAA. Yeah, so at least I was right with that thing. A little bit of pattern recognition there. But like this doesn't tell me much about how to use that thing. We'll need to find examples of actual use of this this trick, and yeah. But I feel like I know a bit more. We also have some kind of study notes, so hopefully that will take us somewhere. And yeah, maybe A makes sense if you want at least one, but no more than two or something. My brain is slowly exploding. If you want at least one, but no more than two. Ah, yeah. So, right. So non-empty maybe A would be A, const, non-empty const with a maybe A. And so it means that it's either nothing, and then you have at least one, or maximum two. Oh boy. Brain exploded. All right, amazing. Thanks a lot for watching. I will be back on Thursday, and we'll continue with this really deep rabbit hole. You can see how deep it is by how right I went, and deep inside the tree I'm going in there. Visual representation of how rabbit holey this is. But yeah, we'll continue playing with this. I think there's definitely much to learn, and starting to become conversant with some of these techniques, especially if we are trying to apply Haskell, things that exist in the Haskell where they don't yet exist in the Purescript world. This definitely, I think, will help deepen my understanding. Also in being more comfortable with this type of inversion, and knowing that it actually is the Yoneda lemma in hiding is also a kind of a nice and warm, fuzzy feeling that maybe all of this will at some point apply to an understanding, a more practical understanding of category theory concepts, such as the Yoneda lemma. All right, that's it for me. Thanks a lot for watching, and bye-bye.